Okay, so we just finished half of our beam. We're going to the next half. So now section CD is somewhere between point C and point D. So somewhere here. There. Uh, Now we are nearing the right end of our beam, and so I will be using the right side of the section. It's quite easier as well because there is no more trapezoidal load at the right side. So I will be using this side of the section. Okay. So the applicability, I will maintain my applicability to be 5.5 to 8. So again, what you would be substituting in the equation is 5.5 to almost 8 or 7.999999. Again, we're still using the leftmost end of the beam to be x is equal to 0 and the rightmost to be x is equal to 13. So how does our section look like here? So you have your 500 Newton per meter load. And then take note that from C to D here, as you can see, you have an upwards 400 Newton per meter uniformly distributed load. And you have a downwards 500 Newton per meter uniformly distributed load as well. So as your classmate have said during class, we can actually simplify the two uniformly distributed load to be just this 100 Newton per meter downwards because 500 is downwards and 400 is upwards from C to D. But take note that in the section, C will not be found, okay, since we have cut between C and D. So this would be, the whole section would have a length of 13 minus x. So take note that, say, we cut here, somewhere here. This whole thing from the leftmost end up to the section here is x. And so the remaining length, which we would be featuring in our section, the right side of the section, is 13 minus x. There. Okay? So, as you can see, I have placed the supports that we solved, EY, ME, and EX. I have already corrected the direction of ME to be clockwise. We would also be putting the 1000 Newton meter clockwise movement since it's applied at D. Take note that we did not put the 250 Newton force in the diagram. Why? Because it acts at C. And we cut the beam between points C and D. So the 250 Newton as well as MC, the 88 Newton meter moment would not be at our section. Okay? So what would be our section? So if this whole thing, this whole length is 13 minus x, and this length from D to E is 5, then this length from the section to D is 8 minus x, 13 minus x minus 5. And then don't forget to put our shear and our bending moment. This time, since we're using the right side of the section, VCD is assumed to be upwards and MCD is assumed to be clockwise. Okay? So once we have completed our diagram, again, what we have to do is to sum forces along y. So negative 100 times 8 minus x, that's our first rectangle. And then 500 times 5 is our second rectangle. And then you have your upwards EY, and then VCD is assumed to be upwards. Simplifying this equation, we get this equation. So it is a shorter equation than if you would use the left side of the section. Then we saw moment. So again, for our first rectangular moment having a height of 100 Newton meter here, so its moment about the section is clockwise, so negative. And then the distance of the centroid of the force is 8 minus x over 2 here. And then for our rectangle with the height of 500 Newton per meter, again, clockwise moment about the section, negative. So 500 times 5. And then the distance of the centroid of this rectangle is 8 minus x here plus 5 over 2 or 2.5. So this is the distance. And then we have the negative 1000 moment, the given moment. And then we have ME, also clockwise. And then EY would have a counterclockwise moment about the section. And the distance is 13 minus x. Don't forget MCD. And we can simplify now the equation. There. Okay, section DE would be the last section. I have also done this in class already, so we would be just running through this section. So again, we're using the right side of the section. So the applicability is from 8 to 13, and this is what our section would look like. So the 100 Newton per meter rectangle a while ago was removed, and we're left with the 500 Newton per meter. Take note that point D is not in the diagram. Okay? So we cut between point D and point E. Okay, my bad, my mistake by putting it there. So since we cut between point D and point E, this 1000 Newton meter moment here would not be included in the diagram. Okay? So we now have all of our supports, and then don't forget VCD and MCD, the same direction as the previous section. And then the length of the section is 13 minus x, same as with the last section, section D. So we sum forces along y, and then here is our equation for VTD. Also, we would sum moment still at the section. So negative 500 times 13 minus x times 13 minus x over 2. And then ME, and then EY, and then don't forget ME. So we simplify the equation. This is what our equation would look like. Okay. So now, this is the summary of all the equations that we have developed from for section A, B, C, D, and E. This is the summary of the equation. And I have placed here in this table the values that we obtained. So how do we obtain these values? So for 0, for x is equal to 0, we use VAB here, and we get 0. We use also MAB here, and we also get 0. And then for x is equal to almost 1.5, so it should be 1.49999, but we can use 1.5. You still use the equation for AB. We would get negative 300. Now, look here. We use the equation VBC again, and substituted 1.5 to the equation because this equation is applicable from x is equal to 1.5 to almost 5.5. What did we get? Take note that we got negative 600. So why is the value different from the previous value? So take note that we have here a concentrated load downwards 300. So negative 300 plus a downwards load, so that's negative, you get negative 600. And then take note that using equation AB and BC, for x is equal to 1.5, we substitute 1.5 to both equations. For the moment, we get the same value because there is no applied moment at B. So that's how you check your solution for shear and bending. The values using two different equations here for AB and BC should converge or should agree with each other. Okay. Next, we will still be using the equation for BC here, V and MBC, at x is equal to almost 5.5. So instead of using 5.49999, just use 5.5. So take note that VC would be 1000 and MC would be 612.5. Okay, now use VCD and MCD to get the V and M at x is equal to 5.5 here, since that's the applicability. And what do we obtain? We have 823.2233. Again, why is it different? Why are these two values different? Why are these two values different? So take note, the difference of 1,823.2233 would be 250 sine 45. The y component of your force from the hanger. So again, there would be a difference in the values even if it's at the same point, 5.5 and 5.5, because of the applied concentrated load. The difference in the moment would be because of this moment here. Here, 88.38835 Newton meter. That's what we solved before when we transferred the force at the hanger to point C. Okay? It's negative, counterclockwise negative. I will explain it further when we go to the area method, why it's negative. Okay? And then, we also use this equation, VCD and MCD, for x is almost 8. So, substitute 8 to the equation. We get 573.2233 and 2269.66992. And then, use the last equation, VDE and MDE, substitute 8 to the equation, and we would get this value. So, see, it has the same value as the previous one, the one where we used VCD. Because at point D, as you can see, there is no applied concentrated load. However, MD would be different. And look at the difference between MD and MD prime. It's 1000. That is the clockwise 1000 Newton meter load. Positive clockwise. Again, I will explain when we go to the area method why it would be positive. Plus. And lastly, at x is equal to almost 13, use this equation, VDE, substitute 13 in this equation, and see you get negative 1926.776695 and negative 114.21356. Okay, we're now going to graph the values.